Hi students, let us discuss this another example in matrix spaces. Suppose our space X is this time equal to R square and we are defining a function D from R square cross R square to R, and we define this function as D x comma y is equal to under root of, so it is x1 minus y1 whole square plus x2 minus y2 whole square. Now before proceeding, you might have gone through this formula in lower classes, especially in 11th 12th class, that if we have a plane and we have 2 points in this plane, and suppose that this point is having the coordinate as x1 comma x2, I'm just supposing, and this one is having the coordinates as y1 comma y2. In order to find the distance between these 2 points, what we do, we subtract this with this and this with this respectively. So, and when we have to find out the distance between these 2 points, and that is given by this formula. So I hope that the formula is clear to you. Now in this module, what we are going to show, if we have a function defined by under root of x1 minus y1 whole square plus x2 minus y2 whole square, we just have to prove that this function will be the matrix. So what we have to show D is a matrix on, so we have to show that it is a matrix on R square, and we know that in order to show any kind of function as a matrix, it must satisfy 4 conditions, and after that we can say that it is a matrix. And then hence we can say, if it is a matrix, then we can say that R square comma D, this actually forms a matrix space. This forms a matrix space. Let me show you the proof. Let us go through the proof of this theorem. Actually it is an example. The very first thing that we need to show is D x comma y must be greater or equal to 0 for all x comma y belonging to R square. Okay, before proceeding, let me make it more simple. If we will suppose this x is equal to as x1 comma x2, and we will suppose this y is actually equal to y1 comma y2, because whatever the point you are going to take in this space R square, that will act as an ordered pair, we know in lower classes. So it will act as an ordered pair. So we have x equal to this and y equal to this. Now we will proceed. Now since we know that we have this x dx comma y defined like this, so since we know that this under root of it is x1 minus y1 whole square plus, oh sorry, it is x2 minus y2 whole square, so we know that this is always greater or equal to 0. Now how it is always greater or equal to 0? Because this under root is actually the sum of the two positive terms, and this is a positive term, this is a positive term. It is actually the sum of two positive terms, and we know that whenever we have two positive terms, and it cannot be less than 0. Okay, so it is always greater or equal to 0. Whatever the value you will put here of x1 y1, you will always get it greater or equal to 0. So thus we can say, it is a very simple, that dx comma y is greater or equal to 0. So this was actually the first condition. Let me write here, this was the first condition. Now in the second condition, what we need to show, that d x comma y is equal to 0, it is true if and only if we can say x is equal to y. Now in order to prove this result, let us suppose we put dx comma y equal to 0. But what is our dx comma y? That is defined by this thing. So it means that we put this equal to 0. So we have that under root of x1 minus y1 whole square plus we have x2 minus y2 whole square. We put it equal to 0, but we know that it is equal to 0, and again because it is the sum of squares of two terms, so it is equal to 0 if and only if we can say x1 minus y1 whole square is equal to 0 and x2 minus y2 whole square equal to 0. So it is only possible if and only if this thing happens. So which is further possible, from here you can see it is further possible if and only if because the square of any term is equal to 0 means the term inside that square is equal to 0, x1 minus y1 is equal to 0, and similarly here x2 minus y2 is equal to 0, which is further if and only if condition that it is only possible if x1 is equal to y1 and from here it is x2 is equal to y2. Now look carefully what you are getting here. So you are getting x1 equal to y1 and x2 equal to y2, means this x1 is actually equal to y1 and this x2 is equal to this y2, and we know that two ordered pairs are equal when their corresponding elements, we can say when their corresponding factors same. So it means that from here we can say x is equal to y. So it is if and only if x is equal to y. So we supposed that this is equal to 0 and we got that is if and only if x is equal to y. So it was the second condition. Coming to the third condition, now what we need to show, we need to show that this dx comma y is equal to 0 is sorry, so this is actually equal to dy comma x. So what I am using here, that is the concept of symmetry, and that I'm going to use here to prove this. Now this dx comma y is actually equal to under root of, we know I'm writing it frequently, x1 minus y1 whole square plus x2 minus y2 whole square, and can I write it also equal to I can interchange y1 minus x1 whole square and plus y2 minus x2 whole square, because we have square so we can easily interchange them. And if this one was the definition of this, so this will be the definition of this. So it is dy comma x. So what we finally got, we got that dx comma y is equal to dy comma x. Coming to the last point of this example, that we have to show, the last thing that we need to show is the triangle inequality. So we know that to prove the triangle inequality, actually what we have to prove that dx comma y is less or equal to dx comma z plus dz comma y. This thing I need to show, but let me write down separately. I will give the definition to this and then this and then this. So if I will define dx comma y as per the metric given, so how can I define this? I can easily write this dx comma y as, I know that it is actually equal to under root of, so it is x1 minus y1 whole square plus x2 minus y2 whole square. Further I can make it simple. Look carefully, I will make it simple. I will just write down it in the summation form, and I will write here xi minus yi whole square and here I is actually running from 1 to 2, because when you put I equal to 1 you will get this term, then plus by putting I equal to 2 you will get this term, but there is a root also, so I just need to put here overall 1 over 2 power. Is it okay? So I hope that you got this point. And similarly, can I write d x comma z as equal to summation I equal to 1 to 2? You can also use here I, or you can use any other index. So I is equal to 1 to 2, but what I will write inside this, see, when I had this x, so I wrote xi. I had this y, I wrote yi. Similarly, I have this x, now I will write xi, and then I will write minus zi. So that will be whole square, and again I will have a power as 1 over 2. Clear? Then last thing, that is the definition of dz comma y. Similarly, I will put here summation I equal to 1 to 2, and I have z here, so I will write down zi minus then yi, and this will be whole square power 1 over 2. Now what I will do, see clearly, I have to show that dx comma y is less or equal to this thing, but I will suppose that it is, and at last I will show that what I assumed is actually true. Okay, now before proceeding, let me do one more step here. That is, if I will put this, you can see here x I minus yi, so I will put it equal to ak plus bk. Let me put xi minus, because there's a reason, yi, I will put it equal to ai. Okay, let me put it equal to ai plus bi. I will put it equal to this. Similarly, you can put here, you can see you have xi minus zi. I will put xi minus zi to be equal to ai. I will only put it equal to ai, and I will put zi minus yi equal to bi. So remember these three conditions. Now it's a little bit lengthy example, but it's a very simple example. Maybe you will not get it anywhere, so that's why I'm just uploading it for you. So see, now I told you that I will assume that this condition is actually true. So by the assumption, what can I say? So can I say, instead of dx comma y, I can write directly this sum is the summation of this thing that I'm going to use here, I equal to 1 to 2. This is xi minus yi whole square power 1 over 2, and that is less or equal to what I'm going to write here, dx comma z, and that dx comma z is equal to the summation I is equal to 1 to 2, and this is xi minus zi whole square and power 1 over 2. Similarly, by adding, and I will write this thing, so this is summation I equal to 1 to 2, this is zi minus yi whole square, this is 1 over 2. Now I will replace the values. I know that I have assumed that this is equal to ai plus bi, and I will write down ai plus bi whole square. So it will be equal to, summation I is equal to 1 to 2, and this is ai minus bi whole square power 1 over 2. It is less or equal to, can use the summation I equal to 1 to 2. Instead of this, you can write down ai whole square, and it is having the power as 1 over 2 plus, and similarly summation I is equal to 1 to 2 bi power 2 and 1 over 2. Now what you will do, you will squaring on both sides. So squaring on both sides, what you will get? So you will get this as cancelled out. You will get here summation I equal to 1 to 2 ai minus bi whole square is less or equal to. So when you will square this whole term, let us suppose you assume that you are just squaring and you will get here square. Now it will be a plus b whole square formula. So give the square to this term. What you will get? It is I equal to 1 to 2 and it is ai square only. Then give the square to this term. It will be summation I equal to 1 to 2 and this is ai square, then plus 2 times this and this, so 2 times twice a b, so it is 2 times summation I is running from 1 to 2 ai square 1 over 2 and summation I is running from 1 to 2 bi whole square 1 over 2. Now it's a simple calculation, so you can expand this thing also. What you will get? It is actually plus here. It is actually plus here. So it is a little bit mistake that I made here. It is actually plus here. So you need to put it equal to plus. Okay, so it was plus here. Put it plus. So this is plus here. Okay. Now I will expand this also by expanding, so you will get I equal to 1 to 2, it will be ai square, then plus summation I equal to 1 to 2, this is bi square plus 2 times of, you will get summation I equal to 1 to 2 ai summation I equal to 1 to 2 bi, and that is less or equal to the whole thing that is here. uh, Let me make it a little bit simple by just assuming that this thing is actually equal to this. Okay, so this is less or equal to this whole thing. Now what you will do, see here, I can easily cancel out this with this thing and this with this thing. So I think this is bi here, so I can cancel out. Now what I am left with, so I'm left with that 2 times sum of, let me write down ai and bi at the same time, because it is a summation in the product, I can make them to combine. So that is less or equal to, now this thing is less or equal to 2 times, actually it is 2 times summation of ai whole square power 1 over 2 and summation I equal to 1 to 2 I equal to 1 to 2 bi square power 1 over 2. You can further cancel out 2 and 2, and the last thing that you will get from here is summation I running from 1 to 2 ai bi is less or equal to summation ai square 1 over 2 and summation bi square 1 over 2. So are you getting this inequality? This is nothing but it is the Cauchy-Schwarz inequality. This is the Cauchy-Schwarz inequality, which is always true. So this thing is always true. It means that what I have supposed, that dx comma y is less or equal to this plus this, is also true. So that is also true. Means all the conditions are satisfied. So we proved that this D is a metric, and consequently you can say that R square comma D forms a metric space. Thank you.